Okay. Hi. Good evening, everyone.
Good evening, sir.
Yeah. Okay. So I think I don't know. Today I think there is OPP for some of the people, right? So
Yes, sir.
okay. Let's say not sure. I'm not sure that whether students will join or not. But okay. Let's start anyway, right? They can watch it later on YouTube, possibly. Fine. So okay. I think where were we yesterday? We have completed this part. I hope all of you understood this part. The dual and
Yes, sir.
correct, right? Yeah. Uh, so now the next part is it's not related to SVM right now. I think it is related to uh, some different techniques, right? So now we are into uh, these two techniques which we are going to learn, which is bagging and boosting, right? So what does they do and how they will work, right? We'll understand about that. But before understanding that, what we have learned so far is there are two types of classification techniques we have seen, right? Which are those two types of classification techniques? One is, or maybe you can say not classification, but in general supervised learning techniques, right? They comes from two types of modeling. One is generative modeling and another is discriminative modeling, right? What is generative modeling generally? Okay. What do you understand by generative modeling? What do you model there? Generative uh, and I think one is discriminative modeling. In generative, what kind of probability you are interested in? Let's say you have data as x data set like this, with x as the uh, data set and y is the label, right? So with that xy, what kind of what probabilities you try to understand, or you try to predict? So in generative modeling, we do find out joint density, right? Joint density between the data and the labels. And in discriminative, we are interested in finding out the probabilities of the label given the data. Is that correct? It is what we try
Yes,
to do.
sir.
Correct. So, and which are those techniques we have seen? Uh, okay. What are generative modeling techniques? Naive Bayes, right? Or Gaussian naive Bayes. These are the techniques where we actually find out the joint densities. Fine. For discriminative, what are those techniques? K nearest neighbor. Then I think we learn about decision trees, right? Decision trees, logistic regression, perceptron, SVM. All of that comes under uh, SVM and perceptron, where we actually try to find out these probabilities. So, given the data set, we try to predict what is the
So
label.
what is that after NB? What you have written? Con B or something?
GNB, Gaussian naive Bayes.
Acha, Gaussian.
Yeah, it's a naive Bayes technique. Only I think we use the Gaussian variables, right? There. In naive Bayes, we use binary classifiers, right? All are the binary variables. For example, what does that mean? You have a feature with 0 1 labels. Gaussian naive Bayes, the features can take any real value, and we assume that they are distributed as a like normally distributed or Gaussian distributed. Correct. Okay, so today we are actually saying the one of the technique which is called as a, or another technique which is actually the classifier technique, but those are the ensemble classifiers or meta classifiers. We'll understand about them, but before that we'll try to understand what is the two important uh, concepts, which is overfitting and underfitting. Overfitting and underfitting. So what is overfitting, what is underfitting? We'll try to understand that first. let us say, okay, first we'll try to understand. All of you know the bias and all of you know the variance, I assume, but try to understand this part first, and we'll see through that whether this is correct or not. Let's say you have a data set like this, right? Is that correct? We have this data set, and this is a supervised data set. What does that mean? We have that xy pair, right? We have the labels. This is during your training, and after training, what you try to find it out? A model, right? During training, you try to find out what is a model which governs this kind of data set. Let us say, or can you tell me whether for this kind of data set, let's say it's a regression or classification data set, let's say regression one, what do you think? Is this a uh, what is, let's say this is y equal to mx, fine. This is what, this is your predicted label, right? Or this is a model which we try to learn here, uh, and there is another model, let's say like this. Fine. Suppose this kind of a I don't know, some polynomial which is maybe quadratic or not quadratic here exactly. It is like cubic or I think fourth dimensional, right? Let's say it is mx to the power 4 or something like that. Fine. Fourth order polynomial is there, or more than that. Let's say. What do you think the error for this kind of data set? The error will be lesser for uh, this this model or for this model, the blue colored one or the red colored one? Blue color
Error
one.
will be less. Error will be less in the second one. Na?
Error will be less for the second, right? So that blue one. And what I think it is, this error, if you look at it carefully, this line actually going through all the data points, or this curve actually is going through all the data points. It is going to fit all the data points. The error exactly will be equal to 0, right? In this case, right? It is trying to,
Sir, could you please explain again?
okay, fine. So let us say, okay, I'll just remove this first. Let's say the blue colored one, fine. uh, let's not, yeah,
Yes, sir.
let us say this is your data set, right? All these are the data points, all these are the data points, suppose. And now I have drawn a line through these data points. What do you think the error should be here? So here, this is the error. Like, let's say this e1 is e2, e2 is e3, is e4, is e5, e6, and I think e7. So the total error is there, right? So what is the total error here? Sum of errors, let's say for all 7 points. Is that correct?
Yes, sir.
So it is sum of I equal to 1 to, let's say 7 in this case, it is ei, right? So this is going to be a sum of errors here. But instead of this, so this is my model, right? What do you mean by model? It is a mathematical formula, or a mathematic. It is a mathematical model. Let's say what it try to do is it will try to uh, learn the uh, what do you think? It is trying to learn the behavior of the data set, right? How it is going to behave. So in this case, uh, okay, I'll talk about that testing point later, but currently what do you think? This is the error right here. If I use y equal to mx, if I use this model, this is going to be the error, right?
Yes, sir.
let us say I use another model, which is, let's say, maybe the quadratic or not quadratic, the fourth order polynomial or fifth order polynomial, like that, right? Let's say, and it is going like this. So actually, it is trying to cover all. Say, fine. Let's say this is like eighth degree polynomial or something like that, or eighth, ninth, tenth degree polynomial. Okay. What do you think the error for this model will be?
0.
There is going to be zero. So what? So for this kind of data set, which model will you pick for the prediction? Suppose you have. Okay. Suppose okay. Okay. This is green point, right? So I'll try to. I have data point which is a test point, right? So let's say this is x test, right? Uh, or let's say x test is here. Suppose here is this x test, right? Which model will you use to predict uh, the label for this x test? This one, the red one, or the blue one?
Blue one.
Blue one,
So red one.
red one, right? So okay, if I choose the blue one, what will be the error in this case? So okay, where what will be the prediction? What do you think? The prediction is here, right? Okay, I'll okay, sorry, I'll mention you this. Okay, possibly. Suppose, see, this is your x, right? Let's say we'll talk about, let's say, only uh, this y, xy, fine, and uh, all are these data points here, right? So this x1, x2, x3, like that, and I have actually plotted it there. So for this data point here, the blue data point, right, which is x test. Suppose, okay, I'll sorry, don't worry about this part. It's not like this. Fine. So, but okay, if I wanted to predict using this blue, the prediction for this point will be where? Here, right? Is going to, what is the error here? This is the error, right?
Yes, sir.
Is that correct or no? Okay, I'll just draw this is little bit here. So the prediction for this data point for blue line is this. This is going to be the prediction, right? This is okay. This is the error between these two, and for the red line, the error will be here, right? So if you think about it, if I use this kind of polynomial here instead of this straight line, uh, what happens here is, let's say, for okay, I'll write down for red colored curve or that line, the training error was higher, right? Is high, but test error is low, correct? And for blue colored line or a blue colored polynomial, the train error is low, correct, right? Low, or I think it is zero in this case, low, but the test error is high. Is that fine? Are you able to understand this part?
Yes, sir.
Right. So this is called as what? Overfitting. So this blue colored line, right? It tries to overfit the model. Correct? It tries to overfit the model. And in case of overfitting, what happens? Uh, okay, I'll just write it down for you.
In this case, then red will be overfitting.
No, red will not be overfitting, right?
Sorry. Blue
Blue.
will be overfitting.
Yeah, blue is overfitting because overfitting in overfitting what happens? Okay, I'll write down here. In case
Sir,
of over,
are you discussing week 5 topics?
no, 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 it's week 11.
So, but this looks like week five concepts, right? Like,
I
rega-
think no, no, overfitting comes there, but it I think it is not like very
okay.
in that manner. It's there.
Okay.
If
So
you
here, whatever you are trying to say is just if we just blindly follow the follow minimizing error, then it
yeah,
may bias it towards its some
not
particular points. We should consider training points separately so that we can ignore the bias, right?
okay. I'll write it down. And bias actually, you're saying is uh, one thing you're saying is correct, but another way it is actually it's not that correct. I'll tell you what
Okay.
I'm trying to say. So overfitting happens when your training error is low and
Test error is high.
test error is high. Is that fine? Correct? That's
Yes.
fine, right? That's what we have seen here, right? This blue colored curve, the training error was zero, but the when I actually, so if you think about it, right? This if you see that data set, it follows a pattern. It's a linear pattern, right? Correct. It
Mm.
actually has to be. Uh, we have to actually model this data point using the linear models. Correct. It's not like we don't need here the polynomial models, right? But if you try to make that error to zero, right? So what are you forcing here? You are trying to overlearn it.
Mm.
Correct. And in that case, what happens is that case is called as a overfitting. So in overfitting, what happens? Training error is low and test error is high, and that is we actually call it as what uh, high variance. Fine, this is high variance.
Sure, but uh, uh,
With
i-
low bias. Yeah, tell me. Yes.
Sir, but let's say there are a lot of data points, let's say 1,000 or
Hmm.
maybe lakhs and 10 lakhs. So
Hmm.
in that case, so how can we exactly say that it is overfitting? Like if it is, if it found a good pattern for a very large data set,
Hmm.
then the probability, the chance that it overfitten or like, or maybe it is biased or like it is just blindly following the like uh, it's blindly following minimizing error. That won't be the case, right? If data set is too large, if it is trained on very large data set, then the
Yeah, yeah.
chances that of overfitting will reduce, right?
Uh, okay, so we will talk about the data sets again, right?
Because you shown example, right? So
Yeah.
you for there you like drawn some 4 to 5 points. Let's say there is 10,000 data points.
Hmm.
So then it is not possible, right, to find a some function which is fitting all the 10,000 data points. Then if data set is too very large,
No, it is
then it
it is
should
possible.
be
No, no,
correct,
no, no,
right?
no. If you try to find it out, you can find it out that function which actually gives you zero error, but that function will be too complex, right?
Oh, yeah, it will be too complex, correct?
Yeah, so it is like, let's say mx or let's say some a1 x to the power
Mm,
15 plus
mm,
bx to the power something like that, right? So that kind
yes.
of thing, but you will be able to find it out. So
Mm,
if you try to make the error zero, see, in linear regression also, if you think about it, what was your goal? The
uh,
goal is to what? Okay, so I think if you learned about linear regression, the goal was to minimize the error, right? So it was
minimize
like
the.
minimizing the error. And what error? It was y minus y hat, right? So basically it
Mm,
is mx, right? Or mx plus b. That was, or I think in this course we have learned about, what is it, beta x or what? Okay, wx, w transpose x, right? I
oh,
think we have learned like this,
yes.
minimizing this error, the squared error loss. But we, what we said is, we are not actually using all functions. We are just taking linear functions, right?
Mm,
Because if you use all the functions, right, they will tend to overfit. Overfitting is what? You're trying to uh, force that error to become zero, right? But if you think about this data set, even if large quantity of data set is there, right? But suppose your data set is like this.
Okay, so maybe there is 10,000 data points, but it will give us 10,000 degree of function, right? So it will be like x to the power
Yeah,
10,000
yeah,
x
yeah.
plus
That
something like
will
that.
happen. So that will
So
happen. So let's
no
say,
matter how data set is large, it will still overfit.
yeah. So suppose this kind of data set is there, right?
Mm, mm, mm.
Right, and what I actually, after looking at the scatter plot, what is your thought about it?
So it should be it is supposed to be linear, but
Linear, right?
it will make it polynomial of very large degree in order to fit there.
So if you wanted to make zero, right, so it will be like
Uh-huh.
something like this or
Mhm.
something,
Okay.
right? That is possible. See,
Mhm.
mathematically it is possible to fit any kind of data, right? That
Yes,
is
yes,
not
yes.
the problem. The thing is, we don't want that, right? So we wanted a
Okay.
generalization, and
Mhm.
in this case the good generalization is what? A linear one, right? So
Yes,
we are
yes.
seeing a pattern. What is this pattern showing to me? Is that there is a
Linear.
line. Yeah, there is a line actually, and this line actually best fit your data, right? Even the error is there. So, but that error is there, and what is that error? If you have the training error, uh, so there is some training error associated with this, right? But still, you will do good on what?
Uh,
Testing, right? So the test error will be less even if your data set is larger, because inherently if you see that, right, this data set have a linear pattern, so we don't need to fit it through any other polynomial here, right? Understand? Or
yes,
if,
it's clear, sir.
yeah, and let's say if you use, let's say, next degree polynomial, suppose it's a quadratic. If you try to see that, let's say it's a quadratic thing, right? But what's happening here? Here I think the training error also will be large, right, compared to this. So if you try more and more, like third degree polynomial, so I think it is like the cubic will be like this, right, something like that. It will, so if you try more and more higher degrees of polynomials, they will try to uh, reduce the error, right? But that error is training error, but are they going to do well on the test? Most probably not. Correct? Fine. uh, See, that's what, like, it is not like exactly true like every time that, okay, what I'm this has to be true. But in general, if you see here, we can see the linear pattern, and in that case we don't need like higher degree polynomials to fit it here, because with that you are trying to fit a noise, right? Because if you see, right, these are the linear. I think if you understand the stats better, right, so in that case, any observations you take, right, they have certain noises involved in it, right? Suppose you go and try to get the prices of the houses. Simple example, right? In that case, what you do is, some manual errors will be there, some other errors will be there. Otherwise, if that kind of errors are not there, right, for the larger amount of data, you can see that, okay, they will follow the correct pattern. So they actually has to follow, let's say, linear pattern, right? You don't need that other degrees of polynomial to fit this data, because then it will not do well on the test data, right? Is that fine? So this is called as
What is our objective is to do it better in the test. Test error should be low, na? That should be the objective.
uh, no. I think, see, the objective here is to have uh,
Both training error and test error should be low, isn't it?
yeah, yeah. So basically, we don't want that training also has to be like two way, right? So there is a good graph actually. Okay, I thought of, I'll just do the underfitting and I'll draw it. But okay, let's say you have this kind of data. Okay, I'll say that. So okay, sorry. So you understand, right? So if I increase the model complexity, what do you mean by model complexity? So if I use higher degree polynomials, right? Let's say this, on the x-axis it is model complexity. What is the simplest model in this case? The linear model, right? or even simplest is the constant, right?
Hmm.
Some constant value. So let's say if I use any constant, right, y equal to 5, so that will be this one, right? Correct. And then it will have you give some slope to that, and then it will be ax will be the or bx will be the next simplest model, and like that, right? So this is what, so as you increase the model complexity, what will happen, that this is your training error. Okay, so the training error will be, what will happen to you, it will
Decrease.
decrease. Fine. And as you increase the model complexity, so initially the test error actually, if you are having uh, the simplest model, right, your test error will be low. And as you increase the model complexity, right, generally what happens here is the test error will start increasing. Correct. Let's say this is your test error.
So there should be a good balance between both of them.
Yeah. So we wanted this spot, right, where your test error also is a minimum one, and the training error also will be the minimum one. Fine. So this is the ideal model complexity we want. It may be linear model, or it may be a quadratic, or it may be the cubic, but it shouldn't be like too high, right? There are issues with the very high complexity also, is that what, it will take more number of computations, right? So the compute power also will be higher with the model complexity, right? That also is there. And this curve also is generally true in most of the cases where, okay, okay, sorry, I think I done it, drawn this graph wrongly. Sorry. The test error for, okay, test error also will be higher, right, for lower model complexities. So basically it will go like this actually. Sorry, this will be like this, and then it will increase, right? Yeah, and then we need this. If I uh, add this, okay, and okay, this is your test error, that is correct. The- is this true?
Sir,
Hmm.
I confuse it now. So
Hmm.
uh, why was the previous graph wrong?
Which one?
You previously draw some
Yeah. So actually, what happens is, if you think about this graph, right,
Hmm?
so this is not correct, because if you have lower model complexity, right? Let's
Hmm.
say if I use this
Okay,
two,
so no, lower model doesn't guarantee you less error, right?
yeah. So that in that case, so let's say if I use this y equal to 5, right?
Uh,
In this case, my x test is, let's say, here. X test is here, right? Still the error is higher. The test error is higher, right? And for this model, the training error is also higher, right?
mhm.
Training. So in this case, training error is also high and test error also is high. So that will happen. Again, it depends not only on the model complexity. It actually depends on the sample size also. So whatever the sample you are having, right? If your sample is too small, then also the issues will happen, and the similar kind of graph will be there. This generally what happens is, if your test error is very high and the training error is low, right? Correct. So this case is actually of high variance. Okay. And if your test error is high and the training error is high, this situation is called as high bias. Okay, high bias. And high variance is associated with overfitting, and high bias is associated with underfitting. So let's try and understand the example for high bias, and then we'll like join it together. These two concepts will connect together, right? Okay, let me draw another example. Okay, sorry. I don't know what is happening here. Okay, just I think it is not responsive. Let me instruments. Okay, is it visible now? Yeah. So we'll see the case of underfitting. Now consider this data set. Let's say it's a data set I'm drawing. Fine. This is okay. Uh, what do you think that if I use, let's say this is the data set I'm having, what do you think in this case the good model will be a linear model or not?
I
Will that
think
capture?
linear or constant model.
Okay, I'll give you two models. One is let's say this, let's say x, right? So I think y equal to 0, right? And another is, let's say y equal to sine of x. What do you think? Which model is better for this kind of data set?
Y is equal to 0.
Y equal to 0.
Y is equal to 0.
Okay, how? Okay, y equal to 0 means this one, huh? X, right?
Huh, huh.
Okay, this is y and this is x, and y equal to sine x. What that? How does that look like?
Exactly like this. The red dots.
It is kind of like this, right?
Hmm.
So y equal to sine x, correct? And this is y equal to x. Y equal to 0 will be your x-axis. Now you are saying that
But
uh,
maybe sin x is actually correct, right? There can be a possibility,
what is
right?
the pattern you see in this data set, right? So that is what important. So let's say if I have the x test here, right? Suppose x test is somewhere here, right?
Hmm.
Okay, x test. In this case, the training error is low for which case? Y equal to 0 or y equal to sin x?
Y is equal to 0. Training error is high.
Yeah, low is for this, right?
Huh,
So low training error and this is high training error, right?
huh.
What about the test error?
That is also low for sin x.
It is low for sin x, right? So I'm just talking about
No,
this
your test is much more closer to sin x, right?
yeah. So here
Yes.
high, right?
Huh,
High test error,
huh.
and here it's a low test error, right?
This is sure.
So in this case, if I use the simpler function,
Hmm.
right, the simpler model, which is y equal to 0, which is I'll draw it again. And this, if I use this model, sorry, correct, right? If I use this model, the it will have high train error plus high test error, right? And it will have if I use this one, which actually correctly justifies the pattern, right, of the data which we are seeing, because for which the train error is lower as well as test error is lower, which I should use it if I use the lesser model complexity, right? In this case, correct. So this is uh, less model complexity, right? And this is high model complexity, correct. So if I use less model complexity in this kind of data set, what will happen? I may miss out on the structure of the data,
Yes.
right? And we are saying that it's a noise, but actually it is not a noise. The pattern, actually, this is the data which is having this kind of pattern. So you are missing out on that. And in this case, if I use the simplest structure, right, that will lead to what? Underfitting. Understand? So you are saying, you are thinking that these are all errors, right? If I use this simpler model, what is happening? We are thinking that all of these are errors, right? But actually they are not. If you think about this data set, they are not the errors. They are our data set actually is following this kind of pattern. So if your train error and the test error both are high, right? That actually is a uh, case of underfitting, and that is we call it as high bias. Okay, so what are the criteria for underfitting and overfitting? I'll write it down. So overfitting is,
Can you slightly go up the
yeah,
slide?
yeah, yeah. Is that okay?
It's okay also.
Huh? Any doubts here?
Yeah, yeah, you can go to the next page.
No doubt, right? Yeah. So I'll write down, like I'll summarize it once more, and then we'll see what exactly it is.
Sir, I
So
think you can continue. We understood clearly what is the difference between overfitting and
yeah,
underfitting.
yeah, overfitting and underfitting, right? So overfitting and underfitting. So the summary is what it is called as high, or it happens when you have high variance and low bias. Underfitting is high bias and low variance, correct?
Sir, one another confusion is there.
Hmm.
So I feel that we should say for overfitting bias is high, right? Because overfitting is biased
Correct.
towards some points.
Correct.
So for overfitting, we should it should be high bias, right? So why it is in reverse order? Or maybe I
No,
am confused.
no, no. Overfitting is high variance, na. This is underfitting, right?
Huh?
Okay, and okay, I think okay that the page has gone now. But
Okay.
what was overfitting?
Overfitting, I remember. Okay,
Okay, let's say,
so it is um, choosing complex model in order to minimize the training error.
yeah. So let's say you have a data set like this,
Yes.
right?
Hmm.
In this case, what do you think that this data actually follows?
This actually follows a linear model, but in overfitting, it will choose some complex model.
Yeah, right. So here, if you choose the complex model, which will actually tries
Huh.
to,
Look like okay.
let's say, go like
Hmm.
this,
Hmm.
right? It will try to capture everything.
Hmm. So now this is biased towards training dataset, right? So
It is
okay.
not like that. This bias term and
So
variance term is
bias is not that bias which we generally mean in English, right?
in English. It's not English bias. It's okay.
Okay,
This is like mathematical bias, which
okay,
is,
okay.
right, the mean squared error.
That bias. Okay,
MSE is equal to what? Bias plus variance.
okay,
Do you
okay, okay.
remember this?
Yes, that
Yeah.
statistics one bias. Okay,
Yeah,
yes,
and I
yes,
think we
yes.
have I think discussed this about this in, I think, ridge regression case, that the
Okay.
weights were there. I told you, right? So this uh, uh, I think for ridge regression, yeah, that penalty, that parameter we lambda, when we were discussing, we said that this ridge regression W, right? So W hat MLE and that ridge regression, which is better. I think we were discussing about that, and
Hmm.
that time we have discussed this. So MSE is actually the squared error loss, right?
Square,
So
huh.
let's say W minus W hat, right? So this is true W minus true W hat. If I just try to find out this, right? This is MSE, fine. That is equal to your bias. What is bias?
uh, expected value of
W, right?
hmm,
Actually, it is this bias, right? Basically, bias square. So
huh,
MSC is actually bias square plus the variance. And what is variance?
mm,
Variance is minus
minus
or okay, x minus expectation, I think. Right. So was what is the variance formula? Um,
I
Expectation of x square minus
right. Expectation of,
x square.
say in this case, w minus w hat square, right?
Yes, sir.
Right. So it's a deviation square, right? And you take the expectation of it. So if you
sir, isn't it something like expected value of first we square and then take expected value minus expected
that
values
also is there,
square, right?
that also is there. That is like expanded formula, right? For that,
Uh,
generally we use that variance formula as like
okay, this is the same, right? Whatever you read, E of W minus W hat the
yeah.
square. Okay, okay.
So what do you write in general? That expectation formula as, I think, or sorry, variance formula as
E
uh,
of x square minus E of x whole square.
expectation of x whole square, something like that, right?
So yeah,
But this is
Yes, sir.
this you okay. This is the expanded one, right?
yes,
Okay.
yes. So fine. So let's say this is going to be, so this is your bias, or this is bias square, right? And this is variance.
Uh,
And see, for any data set, right, this squared error or squared error loss, right,
hmm.
that will remain same, right?
Yes,
So if I increase the variance, right, what will happen? My
bias
bias
will
will
decrease.
decrease, and if I increase the bias, the variance will be decreasing, right? So
Yes,
for overfitting models, what happens is this variance is
it's high.
high and the bias is lesser. Bias is lesser means actually you're thinking that whatever curve you try to fit, right,
Hmm.
the error is actually getting very zero, right? So you are
Hmm.
actually trying to say that whatever the parameter which for this distribution we are thinking about, that is exactly being equal to the original parameter, and we try to decrease the bias there, right? Because what is bias? Expected value of,
Expected.
let's say in that case it's theta hat minus theta, right?
Hmm. Yes.
Original parameter minus this. Let's say if theta
Hmm.
is your parameter for the distribution, right? And when I say the sorry, unbiased estimator, then actually it is equal to theta, right? So in that case we are saying that if whatever the distribution you are choosing here, that will give me uh, or the parameter is actually exactly the same as that of the original data. So we are saying that whatever the parameter for this kind of curve, right? Let's say it is, or entire my data is following this one, but in reality it is not like that, right?
Hmm.
It is actually following this much simpler model. It's not needed for that, right? So we have, but if I choose uh, the this model over this, right, the bias will be lower but the variance will be higher because it will not work properly. But okay, we don't go into the mathematical details here, but this bias, okay, when I talk about high bias and high variance, it is coming from this. Fine.
Uh, got
Yeah. So underfitting is basically, in simple terms, underfitting is when
high
you
bias, low variance.
underfitting is high bias and low variance, and
Hmm.
where you try to uh, go use like much simpler model.
Hmm.
The model complexity is very low in this case, which might not be suited for your data set. And in high variance case, what happens, or overfitting, what happens? It is high variance, and what you try to do there, you use the higher model complexity compared to the or where you should actually go for the lower model complexity. That's it. Fine. Is that okay?
Yes, sir. Clear.
Okay. So now
Say
how?
for KNN, for
Yeah.
KNN can we say that for k is equal to 1, the bias is for the k is equal to 1 is underfit, and
No,
k
no.
is equal to n will be overfitting?
Yes, k equal to 1 is underfit, and k
Yes,
equals
and
to
k is equal to
n.
n is will be overfitting. Okay.
Actually, k equal to n, what will happen? You actually are taking all, right. So and what is the issue with that? So in that case, whenever any X test comes, right, it will predict only that one which is having the higher labels, right? So if your data is 60% of the positive labels and 40% of the negative labels, any text data comes in, what it will give you? Always positive, right? And that is not good in your predictions, correct? So and with one, what will happen is actually it will not be a good model, right? So it's not actually aggregating anything. So k equal to 1 is a underfit model, and k equals to n is a overfit model. Okay, in case what happens to decision tree case? If you go higher and or higher depth, right? Or if you use entire depth to get that, like, or decisions, right? What will happen in that case? You're overfitting or underfitting? Hey, this is the week 11 only.
Sir, I have a doubt. Can overfitting be beneficial sometimes?
No, no, no. Overfitting also is not good, and underfitting also is not good.
No, no, in some specific cases, can it be beneficial? Like, for example,
Huh.
uh, a company said during some, like the puja months or like the festive months,
Hmm.
the sales increases and the other months it decreases. So in that case, the model
Okay,
would be non-linear.
that is a cyclic variations, right? So
Oh yeah,
that is not this case. So that is like forecasting methods. It will use forecasting methods for that. That is different. It is a cyclic variation.
yeah,
Uh,
yeah. Every year it happens. So
yeah,
yeah.
and that is like entirely different study for that. It's not like.
There are also seasonality factor is incorporated.
Yeah, yeah, yeah. So that is like
Uh,
forecasting methods will be there for that. Again, we use regression and all these things there, but it's like we'll have to use it term wise, right? So for this season, and then this season and this season, like that. So you'll have to provide the weighted average methods. A lot of things are there. If you know it, I think fine. Otherwise, maybe I think one of the courses you will learn during degree, but not sure about it. Okay, so okay, let's start with this. We'll talk about that, right? So underfitting, overfitting again. We'll do the discussion. But let's say this bootstrap aggregation, right? What is that? And we'll see that method. What is it? This is called as bagging, right? So what is bagging, and what do you do
so
there?
bagging is also called as bootstrap aggregation.
Yeah. Bagging's actually full form is bootstrap aggregation, right? So I think, okay, it doesn't sound it good, but yeah, it's bootstrap aggregation is bagging, right? And what do you bag here? You bag. Uh, so okay, one of the examples for this is, I think all of you have heard, must have heard it. It is called as random forest, right? Random forest. Uh, so random forest is also called as or this bagging or boosting techniques, right? So they are also called as meta classifiers, or I think meta classifier is not a popular name. The popular name is this one, ensemble classifier. And why it is called ensemble classifier, that also I'll tell you. Uh, so what you do in this case is you try to aggregate. So let's say, as you said, right, for k and n, if you use k equal to n, what happens is you'll go to overfit the data, right? Or you do the overfitting. In the similar case, if I use the decision trees, if I grow the tree full, right, like entirely. What do you mean by entire? If I go to the entire depth of the tree, what does that mean? You ask the
So
question.
then,
Yeah, you ask the question till will will perfectly classify it, right?
yeah,
And what will happen in that process? You might overfit,
yeah, yeah. Overfitting.
correct?
Too
Because
many questions. Yeah,
yeah, too many questions, and that means it will try to so if even if the outliers are present, right, it will try to fit that also, correct?
Yeah.
So
Can you once again explain what is the correlation between the random forest and bagging? I'm not able to get.
no, okay, random forest is one of the bagging technique, fine.
Okay.
So
And what do you do in bagging actually? What do you do?
Yes.
that,
This is
that
begging.
yeah, I'm trying to explain that. So what you do in bagging is so the decision trees are there, right? So what happens in decision trees? Let's say if I grow this decision tree fully, right, they tend to overfit, right? Okay, okay. In random forest, right, it is called as an ensemble classifier. What it does is it will take the aggregates of, let's say you have uh,
Ini kita konda dekho. Baba ke konda bole. Konda de.
okay, so what you do in a random forest, you take the aggregation. So this is bootstrap aggregation, right? What do you mean by bootstrap and what do you mean by aggregation? We'll try to understand. So what you try to do here is you uh, you, you take the aggregation of uh, different decision trees, right? And let's say you have this, let's say four, right, four trees. You take the average of it, and whatever the average of it is there, that you try to say that this is going to be my uh, uh, label, right, predicted label, let's say. What does that mean? Okay, I will try to understand that again. Let's say you have uh, a data set, right? So let's say you have, let's say you have data sets d1, d2, and say you have dm. How this d1 data set looks like? X1, x2 to, let's say, xn, and corresponding labels y1, y2 to yn, and similarly d2 also looks like that, right? Fine. So each of d, let's say d I 1, and I goes from 1 to n. Let's say I'll say this as j. So here it is, let's say uh, j will go from, let's say, okay, j is 1 to n. Do you understand that? What is the setup here? We have m data sets, right? M different data sets, which will have x1 and y1 pairs, right? So you have the data points along with its labels. Is that fine? That's okay. What you do is you apply a decision tree over this data set. Okay, is that fine?
Yes, sir.
Okay, and it's a different decision tree. You will fully grow the decision tree, and what will give it to me at the end? It will give me some hypothesis, right? So h1 is the hypothesis in the sense, here we are saying that the classification, right, in this case. You remember the decision tree, right? How it look like? Any decision tree, you have theta k, right, greater than or equal to some, or sorry, okay, you have, how does it, how it is written as, say fk is greater than theta k, yeah? And you have some, if it is yes, and if it is no, you will ask next question, right? So maybe I don't know if or some other question you will ask based on other parameter, and you would grow it like that, right? And again you grow it here, maybe you stop here, and you say one as this, another you'll say 1 0, here it is 1, and you grow it again here, you ask some question. So let's say this is question, and you stop here, let's say, right? This is your uh, basic decision tree, right? And when I said it is fully grown, what does it mean? You have asked that many questions such that you will be able to get the data set classified perfectly, right? So clear classification has happened. What will be the training error in this case? What do you think? If I say,
Zero. This is all our cluster.
right, it is a zero training error, right? So
Yeah.
does it perform well on the test data set?
No, no, no.
No.
Overfit version.
So in that case, the test error will be higher, right? So
Yeah.
if I fully grow this decision tree, this might lead to the overfitting, right? Fine.
Yeah.
And h1 here, it denotes what? H1 is actually, let's say, for any test data point, right? Okay, it is giving me uh, the classification, right? Fine. H1 is that function. Let's say H1 is that thing. For any test data set, it gives me the simple score. Fine. I hope you understand this part.
Yeah. So,
Okay.
what is this H1 again, sir?
Sorry.
What is this H1?
H1.
Yeah.
H1 is that's what I'm trying to say. It's a function which gives me let's say if you have X test, right? In a test data point, what will be the output of it? Either plus one or minus one, right?
Oh,
It will let's say it is plus one in this case. For there is one test data point, and if I ask that, or if I use that test data point using that decision tree, right? So its answer is plus one in this case. Fine.
okay. Okay.
So what is the difference between this H1 and Y1? Because the Y1 is level, here is
Y1
also
is
level,
the
no?
no, Y1 is actual label, no? H1 is a
Actual
predicted.
level, and this is a predicted level.
Yeah, this is a predicted label for a test data set, right?
Okay, okay.
For this test data point, this is my predicted label. Fine, right? Okay. So I take this another data set. So we are assuming that here is that all of these data sets are coming from the same distribution. This is fine. This is okay to understand. Coming from same distribution.
Yes, sir.
Fine. So, and then you apply decision tree over that, and then you get some H2 for the same data point. We are actually using the same test point here, and uh, what we are just doing it, we are training my decision tree on different data sets. Is that okay? This setup is understandable, and you take, let's say, HM. Is that fine? So you get H1 H2 to HM, that kind of uh, uh, okay. So this will also give me plus one. Let's say this gives me label as, oh, not zero, I should take minus one in this case, minus one, and in between also you get sub labels. And what you do finally, uh, you how in bagging case, what you do is you take all of them and you average it out, and so that is h star of x, right? X, or I'll say that in this case x test. So the prediction is the average of all, right? So let's say sine of uh, what is the average here? 1 upon m. So what will be the average of, in this case it is plus 1, or okay, let's say I'll not write plus 1 plus 1, I'll write only uh, 1 plus 1 plus, let's say, 1 minus 1 plus 1 minus 1, and up to, let's say, minus 1 divided by m. And whatever the sign for this is there, right? So suppose it is, this comes out to be, let's say, minus 5 by m. So what will be the prediction in this case for the test data point? Minus 1. Understand? This setup is fine.
Yes, sir.
Correct? Is that okay?
Yes, sir.
But in this case, the what is the issue you can think of is, do you have these many data sets from the same distribution? In general case, what happens is you will not have that different data sets to train on the decision trees. What you do in that case, you will have only single data set which we think of it is coming from some distribution, right? uh, but then how we should use this? uh, okay, this actually is doing good for me, because we are taking the decision tree, we are fully grown those decision trees, and we are taking the average of uh, average from all of them, and we are using it for classification purpose in this case, right? But in real life what happens is we do not have uh,
So can
that
you
many.
just take the pace slightly up? Last part I could not understand. Yeah, yeah.
Okay.
Here you are saying that this is basically the sign of 1 by n and
Yeah.
h1. So this is basically whatever plus or minus on whatever you get.
Yeah,
You
you have,
that is basically the sign is basically plus or minus is what is the h
correct. And
test.
that is, this is my the prediction, final prediction. So for X test, right?
Okay.
So what you are doing is you have your, okay, the setup is like this. You have X test, right? I need to predict it's whether it is a label is plus one or minus one. Okay. So what you do is we need to use the decision trees. But what you do is you take different data sets, right? D1, D2 to DM, and they are coming from the same distribution. What you do is you train uh, this data set using the or you train this decision tree using these data sets. You find out its prediction for X test, right? Is that fine? You have, let's say, 10 different data sets. You use 10 different decision trees, right? And you get the prediction for the six test. And what you do is the final prediction will be the average of this. Uh, is that understandable? If not, then maybe I'll try to explain it once more. With the, let's say, I'll take some small numbers.
Well, okay.
Huh? Is that fine?
Yes, sir.
Right. So, but in reality, what happens is we will not have uh, different data sets, right, to train on. What you have is you will have a general data set which is like this: x1, y1, x2, y2, and let's say up to xn, y1, yn. So, how to use this, uh, or how to train different decision trees on this data set, is that then it comes the bootstrapping. And bootstrapping is what? Bootstrapping. Bootstrapping is sampling with replacement. So we'll try to understand that. Uh, what you do is you take this data set and see, I you always have, let's say, 10,000 of data points, or let's say 1 million of data points, or whatever numbers, but we do not have uh, different data sets. We are having one, let's say we have the thousand data points in a data set along with their labels. I need to use a decision tree, but that two different data sets, right? In real life we do not have. What you do is you sample it with replacement. Again, what do you mean by sampling with replacement? We try to understand that. Suppose your data, let's say some data set is like this. You have 5 points: x1, x2, x3, x4, and x5. Okay. And I need to uh, okay, in this case actually bagging comes from this way. Let's say your data set is d1 and d2. I need to get that data set d1 from this capital D and d2 also from this capital D data set. Let us say this data set we consider it as a bag. Okay. And I need to choose how many data points again? 5 data points. And when I say sampling with replacement, is this fine? Let's say you have a bag, your data set, first data set is like this: x1, x2, x3, x1, and x2. Is that fine? Is this data set
Yes, sir.
possible from this points?
The replacement means
Yeah,
we are
replacement. Yeah, we are actually taking one point and we are keeping it back. So that means we are allowed that data set to appear again in your data set, right?
Yes,
So what you are doing here is you have this 5 data points. You randomly pick one data point. Fine. Let's say that is x1. Fine. So we are not removing that x1 from this original data set. The next time when we pick the next point, right, x2 or next random number from this 5 points, or 1 point from this 5 points, we it is allowed that x1 to come again. Fine. Sampling without replacement is what? Once you chosen that point, right, that number will not allow that number to again reappear. Fine. So
yes, sir.
in bootstrapping means what? Sampling with replacement. So d1 happens to be like this. It can be possible that it is x1, x2, x3, x4, like that. So let's say d2 is like this: x1, x2, x3, x4, and x5. Right. Let's say you have another data set d3, which is x1, x2, x3, x3, and x3. Is it possible? Yes, right? That is possible. Like that, you have now you'll get like different data set, and what to do over them? You apply a decision tree, right? And what this will give to me? It will learn something, right, from this data set. And let us say I have one test point, which is x test, right? The prediction for that is here, it is h1. The prediction this decision tree 2 gives is for this x test as h2, and for this, let's say, h3. And what you do then? You average it out, and its sign is actually the final uh, what prediction, going to the prediction for x test. I hope you are understanding this part. So every time, let's say you have n data points here, right? What should I do here? I should get d1, d2, uh, d3 data sets, like that, and maybe so many data set up to, let's say, m data sets. I have taken m data set. But what will how many data points this d1 should have? N data points, right? So so original data set is having n data points. I should have n data points into d1. I should have n data points in d2. I should have n data points in d3, and I should have n data points in dm. But how should I get n data points from this? Is by using this technique called bootstrapping, where we say that it is sampling with replacement, like this, right? So we are allowing this data points coming again into my data set. uh,
So this value of 5, you take only x1, x2, x3, x4, x5. So
uh,
this 5 is a predetermined, or how it is arrived?
no, it is like it's a training data available to you: x1, x2, x3, x4, x5, right? This training data
Mhm.
available to you. So for example, you are doing the house price prediction, right? Or let's say yeah, okay, what is the simplest one you think of? House price prediction is fine, right? Or in that case, okay, what is a better uh, classification? What do you think in?
So my question was, should we take x1 to x2, x3, x4, x5, or I should take 5, or I should take 6, or I
Six,
should take 7?
what is 6, 7?
So you have taken x1, x2, x3, x4, x5. Am I right? So the 5 data points you have taken.
No, no, no. Okay, good. Okay. This is different. Okay.
Sir, this points being repeated, is that on my wish? Like I choose, right? Which points to be repeated?
Yes, yes. So, okay, I'll tell you. Okay, maybe I'll just do it again. Okay, the confusion is, let's say, okay, this is my data set. Suppose x1, y1, okay, x2, y2. These are the data points, right? And let's say up to xn, yn. Fine. Now I wanted a m different data sets, right? To be trained on the decision trees. Let's say d1, d2 to dm. And I said that each of these data points should have how many points? N points. Right? So how these n points come from this data set? So I'll sample them, right? So let's say the sample is like this: x1 y1, x2 y2. Maybe next time it is coming as x1 y1 again x3 y3, maybe x2 y2, then x5 y5. So we are choosing a data point, one data point each time from uh, this data set which I am having during our training, and you choose it randomly. But how many times you should choose it? N times, right? If you have n data points, and that's how you create this data set D1. This example I have given this x1, x2, x3, x4, x5, right? Is to understand it, like simply understand it. Let's say you have five numbers.
So here are five data points. So why are there three clusters or
Huh?
three bags? There are
Sorry.
five data points. There are five data points. You said that until dn.
So we have chosen this five, right? N equal to five here, right?
No, no, I'm saying about this D1, D2, and D3. There
Yeah,
won't be
that
D4, D5.
no, no, no. It is not. It's not like DM and DN should not be the same, right?
Oh, so how do we choose how many bags should be there?
No, no, Abra, please try to understand what he's saying is that x1 to xn are the points.
Yeah,
In the D1, you take all x1 to xn. Say n is 20. So in D1, there will be 20 points. So
yeah,
Okay.
out of these 20 points, the number x1 might repeat two times or three times.
yeah.
A total will be 20. Total
Correct,
will be 20.
correct.
Total number of points
Yeah,
will be
yeah,
20 in D1.
20.
yeah,
And
I get that. But like I'm saying that how
so
many bags?
no, no. That is it. It's up to you. It may be five.
Acha, acha. Yeah, that's up to me. Yeah.
Yeah,
Okay,
it
understood.
it might be 10. It might
And
be
in
5.
every bag, I can repeat all the points, repeat some
Correct,
points, and
correct.
that's not good. Yeah,
Correct.
but the
These
total should be
these five buckets, these five data decision trees, DM is equal to five. Is it a
Yeah.
predetermined or how it is arrived at?
no,
DM
no.
should be five or six.
That is also the kind of a hyperparameter. Like
That's a
Hyperparameter.
hyperparameter. Okay,
yeah, it's not
understood.
like, yeah, it is not like compulsory you need that many only. It can be like anything. You can have lesser, you can have higher, but I think see if you, but what it gives me, what it gives me is that it actually reduces the variance, and that is what we needed actually, right? So what we are trying to do here is you sample this data points like this. Sample, how you sample here? Sampling with replacement, right?
Then, sir, over here, if one point is repeated multiple times,
Yeah,
this might also increase the risk of overfitting, right? By
correct,
reducing.
right,
Yeah.
right, that's true. But now uh, what is the chance of each point repeating? Let's say you have n points in a data set, right?
Yeah.
Right, if you have n points in a data set, uh, and if you are picking it randomly, right, that also is there. So random is kind of uniform, right? What is the chance
Mhm.
that let's say x1 is chosen randomly from n data
One
points?
by n, one by
One
n.
n, right? Fine. And we wanted to see that in each data set how many times it will appear. Correct?
Okay.
Correct, right? So
Yeah.
okay, what is the chance that it will not appear? First place. Okay, how many data points you are choosing here in your D1 bag?
N data point.
N data points, right? Fine.
Yeah.
Okay, so maybe I'll just do it properly that everybody will understand. So you have total of n points, correct? N points. You have and that in into a data set D. Let's say I have chosen a D1 data set from here, right? With replacement, and
Mhm.
uh, I have x1 as a 1 point out of this data set. What is the chance that uh, it will get picked from this D, right? The chance it
One
will
by
get
n.
picked is 1 by n.
Okay.
Now, what is the, so I need to check whether what is the probability that it will appear multiple times into this, right? Correct.
Mhm.
So
Yeah.
okay, uh, what is the probability that it will not appear in this data set?
It will not assume
Yeah, let's say okay, you have how many positions?
n position.
N, right? N positions. Uh, let's say for the first time it will get picked is 1 by n, right? There's a
Huh?
probability it will pick 1 by n. Like that,
One
it
by
is
one by
right, but it will not
one by
get
n whole to the power n.
but it will not get picked is.
One minus one by n. Yeah, yeah.
So for if I choose n points and it will not get picked into that data set is how much? What is the probability then?
One minus one by n whole to the power n.
Yeah, so 1 minus 1 by n to the power n, right? It is not
Yeah,
picked. So
yeah.
it is actually there in the data set. What is the probability? So if I wanted to find this probability that this x1 point is in the d1 is how much? It is this, right?
Hmm.
Is
One
it?
minus.
So that
Yeah,
means
yeah.
x1 is there in the dataset d1. The probability that x1 is there in the dataset d1 is this one, right?
So it's basically one by n to the power n.
Correct, right? 1 minus 1 by yeah. Why I have written it like this? Okay, that is the specific thing is there. If you remember the limits, right? So limit as uh, or x tends to infinity, and this 1 minus 1 by n to the power n, right? This is basically 1 by e. Correct, right? If you I don't know if you guys remember this formula or not, but
Yeah, yeah, yeah.
so
There
this
was a formula.
the,
Yes,
the
yes.
limit it
Of
goes
this
to that,
formula.
right? It is
Uh-huh.
1 minus c. 1 minus 1 by n to the n is 1 by e. And
Uh-huh.
if you just do the uh, calculations, this is 0.33, I guess, and that is going to be 0.67. So there is a 60%, 67% chance, right, that it will get
It will appear. It will
it will
appear.
it will appear or it will get repeated actually, right? It should be there in the data set, right? There is 67% chance that it will appear. So that means what? And that okay, again, this will happen when this probability is happening is when n is large, right? Because this is true for n tends to infinity, correct? That limit is actually existed when n is actually tending to infinity. So that means one thing was clear, right? If it appears again and again, right, actually the variance will be higher, correct? if
Uh-huh.
if it is repeating so much, like so more, the variance will be higher. But what we are seeing through the probability is that it is not the case, right? There is 67% chance that it will appear once, and 30% chance that it will reappear again, right? It's kind of saying like this. But again, how this will decrease if I average it out, right? So what I'm trying to do here, even though that chance is there, we are not only relying on that, right? We have d1, d2, d3 and d5. Fine, we take their we use these data sets for the decision trees and we average it out. Is that okay? we a- so finally what you are doing is you are
That,
doing
that means probability of not repeating is 0.33 or probability of repeating is 0.33.
0.33 is probability of repeating.
Repeating and non repeating is 0.67.
So it's a higher probability, right?
Non repeating is 0.67.
Yeah, non-repeating is 0.67, and it will repeat in 0.33.
0.67 is not the probability of like it is the probability of occurring, right? You said because we found out this
Yeah, but
one minus one by n is
no, it is
not
there.
repeating.
Yeah, that's true. But it is we have found out this probability x1 into d1. So that means it is there in the data set, right?
Ha ha ha.
Actually
It
coming from
belongs to the data set.
it comes actually once, right? So next
Ha.
time it will appear again. It will take. So if you think in that way, right? It's like 33% chance that it will not. Sorry, it will repeat, and 67% chances that it will not repeat. Kind of saying like
Okay.
that. Fine.
Oh, okay. Oh yeah, yeah.
So what? But again, see, this is a good probability. Again, when you average it out, right? Because the final prediction is not only based on d1, right? It is based on all d1, d2 to dm, and when you do that, right? When you aggregate them or average it out them, what will happen? This will so yeah. So yeah, a lot of actually questions might be there, right? Whether it will work or not, but in practice it works. So this bootstrap aggregation, what is bootstrap in this case? Bootstrapping is sampling
with
with
replacement.
replacement. Yeah, that is bootstrapping, and aggregation is this one, right? This is aggregation step.
So, sir, how is this helping us? Can you explain?
What is it? What
How
are
is it helping us in our like computation or decision making?
yeah
How is
so
it?
so in decision so this is a random forest, right? So random forest, how it does it, random forest is actually it is called as the ensemble classifier, or and what it generally you can actually take out different classifiers like decision tree, maybe linear regression, logic regression, or like that, and you can take their predictions and use it to aggregate. But in general random forest works on decision trees. Fine. So what you do is you take uh, you actually sample the data set, right? You sample the data set in different bags, let's say, and then you find out and you grow the decision trees over them over this data set separately, and if whatever the final predictions will be there, you just take the average of them, and that will be your prediction, and generally it works well in practice. But this decision trees which you are using, right, they should be fully grown, right? So that means they are overfitting. So you take like overfitting decision trees, fine, and then average them out, and actually in reality or in practice, right? In practice, it will reduce the variance. So this see this will, right? So this will see, or this effects actually you see when you work with like uh, uh, work on a data set,
So,
real data set.
so in the like in normal decision tree, we try to set all the data points and ultimately overfit the data. And
Correct.
here also we are kind of overfitting, but by replacement, by replacing the same data point and then averaging it out, right?
You are sampling it, and now you have different so it will learn differently, right? So
Yeah,
if
yeah. We have different bags and then we average. Yeah.
yeah,
Okay.
so for example, the smallest example is here, right? So here when you learn how many data points are here, you think x1 x1 x2 and x3, so only three are there, right, out of 5. So this
Yeah.
decision tree when you grow, it will not actually taking into account the effect of x4 and x5, correct? Here you are actually using all. Here you are again leaving x4 and x5 like that, right?
Yeah. So
And
it
now
kind of all balances out at the end,
yeah,
right?
yeah. So the idea behind this bagging is you should be able to get the reduced variance, and actually in practice it happens like that. Fine. So we mathematically we can't prove it, but in practice actually it happens. Okay.
And that about that hyperparameter, like how many bags we choose, how do we determine that before actually seeing, like after we see the data point, how do we determine that these many bags we might need to compute?
So
Like that?
how generally, okay, how do you do that is, okay, you know the cross validation technique, right?
Uh-huh.
What is cross validation technique?
Yes. So we choose and then see
So you
and
so
validate it, cross
whatever
validate it.
the data set is there, you actually use like 20% of the data for the validation set as a validation set, and 80%
Yeah, we,
right?
yeah, yeah. And then we, yeah.
Yeah, so what you do is you take 80% of the data, then do the bootstrapping over it, fine, and then
Oh.
use the decision trees over that, and use that validation set to check how much error it is getting, fine. And in that validation set, you know the labels also, right, already.
Yeah,
So
yeah.
whatever the final validation error and the training error is there, so for what combination of that, right, like decision trees, right,
Mm-hmm.
it gives the lower validation error and the lower training error, that that m you choose, right, that many decision trees you need to grow, fine. And I think that will be the final answer, right? Cross
Yeah.
validation techniques works like that way, and then you test
So
it out.
is there any name for this hyperparameter?
Sorry, no, no, no,
Is
no,
there any name for this hyperparameter M?
no, no,
There is no such name. No?
no, no name.
So this method is called ensemble aggregation, or this is
ensemble classifier, or basically it is random forest is ensemble classifier, or you can say that uh, and this method which it is used, right, it is called as bagging. Why it is called bagging? Again, we use the bags, that also is there, but mostly it is bootstrap aggregation.
this thing is only ensemble, right? Ensemble aggregation also.
Yeah,
That's
yeah, yeah. Ensembling means what? You are actually adding different things, right? So you are ensembling decision trees here, right? You have m decision trees, you are taking their effects, m decision trees, different decision trees on the same data set. Okay, these are
right.
just the names, and then another method is it is called as the boosting method. Boosting, and in boosting we have different boosting algorithms, but in our syllabus it is there, which is adaboost, and this is also the popular uh, actually it's what a lot of people use it in the reality, right? In practice adaboost also is people use random forest very commonly. So again, what is the what is the goal in this case, or how does this works is, it is an algorithm, right? Adaboost is an algorithm. What it does is actually convert the weak learner into a strong learner. Fine, that is what how uh, it is mentioned. So what you do is, you when you see when you take the decision tree fully, it is trying to overfit, right? Correct, it will try to overfit. If you use decision tree, or like let's say if you don't grow it fully, you just do it, one thing is like, let's say you ask a question, is this than theta, and you just say that based on only one question, you predict the class label, right? What do you think, what will happen here? It will overfit or underfit? It will underfit, right?
Sorry, sir, could you repeat?
See, if you see, if you have a data set, and if you apply a decision tree over it, and if you apply it fully, full grown, right?
Ha,
So
ha, ha.
you ask so many questions such that each of the data is getting perfectly classified, right? Then
Yeah,
that case it
that
will
is,
overfitting.
hey, overfitting, yes.
Correct. But instead of that, I will not ask so many questions. I'll ask only, let's say, I ask only the first question, one question, suppose.
Hmm.
Hmm?
Hmm.
F case theta, and based on that question only, we classify all the data set
Okay, then it is underfitting.
underfitting, right? And or if you use, let's say, one or two levels later, then so this underfit, so this is weak learner, right? Is it learning
Yes, yes.
properly? No, right?
No,
If you
no.
use only one question, it will not learn, and this is called as a weak learner. Generally, this kind of uh, weak learners are called decision stumps. Okay, they are called decision stumps. They are not decision trees, right? Decision tree is like you ask
Yeah,
series of questions until you get like uh,
there are multiple levels.
correct, right? Multiple levels. So if you use only first level, one level or two levels, they are called decision stumps, and they are generally are weak learner, correct? Because
Hmm.
they have not learned much. They are just like weak learners. What are
Also, there might be a possibility that there are at most two questions that are needed to correctly classify them. Then it can also be a strong learner.
yeah, but in general, what do you think? Like if you have like
Yeah, in general,
said with x, if your xi is in RD, right? If your dimensions are too high, right? So xi is in
Mhm.
RD. That means, let's say, if you are trying to you know find out the body mass index for the any person, right? And if your attributes are like name, age, gender, height, weight, all of this, right? In that case, these things are so many, like the variables are too high, right? In that case, it will not work anyway, correct? With
Mm.
one simple question, you will not be probably able to classify it correctly, and in reality it will not, right? Or in practical purposes it will not. So otherwise, then there is no use of this machine learning there, right? If with only one question, if it is able to classify properly, what it does here is I'm writing hello. Am I audible? Yeah, Disha. Hello.
So your voice is low.
Hello. Yeah, I'm actually using my full voice, but I don't know. Is it fine now?
Yes,
Okay, I'll write down the adaboost algorithm, and then we'll try to see how it will work, right? So let's say it's called adaboost. Adaboost. Ada is called as like adaptive, right? What else we have seen earlier? This adaptive kind of thing, gradient descent, right? Gradient descent is also iterative algorithm, and there also actually we use the adaptive gradient, but that is not in our syllabus. But there also you use the adaptive. Adaptive means you try to learn it from the previous step. It's kind of like that. This is an iterative algorithm. What it does is I will try to understand. Let us say your data set is like this. So okay, I'm using the same notations as there in the lectures. So this data set is like this: x1, y1. So let's say xn, yn. Fine. And each of xi is in rd, and each of yi is in real. Okay, not real number in this case. If we are using the classification, it's +1 or -1. Done. What you do is you initialize randomly first. You initialize uh, randomly. D. O. D is for here. What is it? D here. It stands for uh, okay. I'll tell you. This is this. I think you know it's iteration, and this is 1/n is what? It's a weight, right?
yes, sir.
This is a weight. We are actually like saying that each of the data points will have the same weight. Fine. Or each of this descent trees will have the descent terms will have the same weights, right? Fine. Now what you do is you do the iterations for I equal to, or not for I, for t equal to, 1 to t, and ht is a ht is what? So decision stump, or decision stump. This case it's, or it is a weak learner, right? Weak learner. And this is the input, is going to be the input, which is, what is the input here? Entire data set, and that whatever the weight associated with at that step, t step, right? Okay, and what is the output for this? St will be the output, right? What will be the output here? St gives plus or -1, right? So now what you do is, in the iteration process, what you do, if it is a weak learner, right? If it is not able to correctly classify the data point, you change its weight. Initially the weight was 1/n, right? For that weak learner. Now you change it to the next step as t plus 1 for that ith, let's say, data point, it has to be equal to the previous weight multiplied with e to the power alpha t, and if ht of xi is not equal to yi, and dt of I into e to the power minus alpha t if it correctly classified the data set. What are you trying to do? Are you understanding anything here?
Where do this exponential function come?
This is what, like, this is okay. This is an algorithm, right? So this algorithm says is like we assign, or okay, if I use the positive weight here, what, okay, positive value here, what will happen? Or e to the alpha t is, let's say alpha is positive and the iteration step is positive, right? In that case, we are increasing the weight, right? Original weight.
Okay.
Okay, so it's not like coming from somewhere. It is like this algorithm is like this. So
Okay.
the person who have designed this algorithm is, it says that if you incorrectly classify, right, what you do is you provide the higher weight, fine, and if you correctly classify, you provided a lower weight for that distance step,
The,
right there. And then what you do is you, at each step, what you do is you normalize these weights. Is that fine? This is what the algorithm is, and what will be the final decision? X at any t step is, that is again sine of summation of t equal to 1 to t, and alpha t ht of x, right? And what is alpha t here? Alpha t is basically, it's this quantity. It's like little bit complex, but I'll tell you how is that quantity. It's like, say, error of ht divided by error of ht. In simple, okay, this is what actually in the lectures it is written as, but you can think of this alpha t as like this.
can you take the slide slightly up?
Yeah, just a minute. I'll find, write it down it properly once, and then it's like 1 minus epsilon upon epsilon. Epsilon is the uh, error you make, half epsilon. Fine. Okay. Now this is my algorithm, entire algorithm. Yeah. Now tell me, what are the doubts? We can take it here. This is my algorithm. Uh, okay, maybe we can, maybe in a solving the session, right, we can see the examples over it, but I'll try to give you the understanding how to, how does it will work, right, in practice. So let's say uh, you have a data set like this. I'm taking the simple data set like 50 comma 1, let's say 40 minus 1, uh, and let's say 30 minus 1. Fine. This is the simple data set. Let's say my h1 is the, it's a decision stump which says if uh, x is less than, less than, maybe less than or equal to 40, or let's say, okay, not less than or equal to, say if it is greater than 40, I will say it as plus 1. And if x is less than or equal to 40, I'll say minus 1. Okay. And there is another decision step which says h2 equals to, if x is less than, or okay, if x is greater than 30, I'll say plus 1. And if x is less than or equal to 40 or 30, so 30, I'll say that it is minus 1. So this okay? This setup is fine. Does this look like a decision stump?
Yes, sir.
Right? And okay, this is, by the way, this is plus 1, this is minus 1. So these are the labels and this is the data points. So h1 does how many mistakes and h2 does how many mistakes? Can you tell me? Say this is my x1 y1, x2 y2 is x3 y3. What does h1 do? How many mistakes it does?
0 for X1.
0, right? And what about h2?
Okay, one mistake.
One mistake, right? Right?
Yes, sir.
So initially, what we are saying is the aggregation. Okay, the output should be what? H1. Let's say alpha 1 times h1 plus alpha 2 times h2, kind of like that, right? And it has to be like the aggregation should be sine of this. If I take, right, uh, then that has to be my final output, right? So h1 does the 0 mistakes and h2 does 1 mistake. So what my algorithm says here, okay, and initially in the initial step what you do is you take, let's say, the 1 by n. So let's say you have the two stumps here, let's say, or three points, right? So each of the points will have how many, what is the weightage? 1 by 3. Fine. So what
Yes,
will be the error in the first, for the first decision stump, h1?
0.
1 by 3 into x1 is 0, 1 by 3 0, so 1 by 3 0, so it's 0. What about the error in the second decision stump? It is 1 by 3 into
0.
0 plus 1 by 3 into,
1.
here, here it is doing mistake, right?
Yes, sir.
Yeah, so it is 1 plus 1 by 3 into
0.
0, so it is basically 1 by 3.
But you told the error part is half times log 1 minus error by error. Yeah, this one alpha t
No, no, it's epsilon, right? So I have written it epsilon here, the error of
error,
h1.
no? Is
Yeah,
error.
this is error, right? So now
Yeah, this
here,
error is in first case it is 0, na?
first case is 0 and the second case
So
is,
if you put 1 minus 0 by 0, what will happen?
no, 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 no. So in that case, you actually, okay, fine. 1 minus 0 by 0 in this case, you're saying, right? So if you think, right, I think ln of infinity is what? Uh, it's,
1 minus 0 by 0.
actually, see, we don't take the, we don't take the, I think we don't take that, we take the normalized error, I guess. But okay, fine. In that case, also, I think ln of infinity also, I think it's 0, right? I'm not sure about it. Uh, okay. Okay, but okay.
Log of infinity will be 0.
No, no, sorry, sorry. Okay, I think I'm doing some mistake here. Let us say, okay, dt of I to the power e to the power alpha t, and this one, right? Alpha is coming from here, correct? And this e to the power alpha t. Okay, I think this. Okay, maybe this example is not suited to this, or one by, what is ln of 1 by 0? Is it
Ln
one?
of infinity should be 0, na?
I think it should be 0. I'm not sure what is the value of it.
Yeah. And if it is 0,
0.
then we are putting one third, na?
And for the second stump, it will be what? This for second stump, right? This is h2 and this is for h1. The error for h1. So now we will look into this part. Let's say, okay,
Okay.
you just think about h2 now. So what will be your alpha? I'm just, I didn't have the example with me actually. I just formulated it here. So maybe the values might not match. But let's say the alpha should be here. In this case, it's half ln
Half
of,
times, yeah.
I think it is,
1 by 3. 1
uh,
So
minus
1 minus 3 minus 1, 3 minus 1 by 1. 3 minus 1 by 1, na?
yeah,
Out of
1.
3, 1 there is error. 1
Yeah,
minus error.
besides, let's say
1 minus, yeah.
we'll do it. So it is basically it's
Oh,
2 by 3 by this one, right? So it is 2, right? The ratio is 2, right?
yeah.
So, and that means if I take it like so it is like, okay, half ln of 2, or I can say that
Yes, yes.
uh, root of ln of 2, right? Some kind of this.
Yes.
And then what you do is you for the next iteration you plug in the value here, correct?
Mm.
And the initial, so the updated uh, weights will be what? For the first one is it doing the mistake on the first data point there? No, right? Yes,
No, it is right.
so
No, sir.
it was correct. So uh, it was correct. That means this is this,
So
right?
you should take e to the power minus alpha.
Yeah. So for x1, it will be 1 by 3 into e to the power minus whatever the alpha, right there, alpha. And let's say it's the second iteration or the first iteration. Let's say it's first iteration. After the zeroth iteration is the first iteration. So for x1 it is 1 by 3 e to the power minus alpha. For x2 it is making mistake, so it is e to the power alpha, right? 1 by 3 e to the power alpha. And for x3 it is 1 by 3 e to the power minus alpha, right? Correct. This is my uh, d1 tilde of I, right? Is that okay? Hmm? So what next we will have to do? We have to, so we have to take the normalized thing, right? So normalized weights. So what will be the normalized weights? So
Slightly take the page
yeah,
up slightly.
yeah,
Next, next, next.
next page.
Down, slightly down.
Yeah,
Yeah, yeah. Next, next. The calculation, what you yeah.
here.
So down, yes, yes, yes. So that one third.
Uh,
So how are you getting this one third?
Error, it does error on this one, right? Let's, okay, don't
That's a state
worry about,
one error out of three.
yeah, don't look at h1, let's say, right now.
Okay, okay.
Okay,
One
just
error out of three.
one error out of three. So this is 1 by 3, right? And then
Cheek.
you take the alpha as a root of ln of 2, correct? Then for or which data points it does actually the mistake, right? So you take that, so it will be 1 by 3. It's the x naught, right? So that is your d01. It was 1 by 3, right? D0 of 2. So basically it is x1, x2, x3, right? For each of the data points, it was like this. So now updated one will be 1 by 3 e to the power alpha, right? Minus alpha. Then here it is 1 by 3 e to the power plus alpha. Here it is 1 by 3 e to the power minus alpha. Now the updated weight, right? The final updated weight, normalized updated weights will be. So these are, okay, maybe I'll just do it like this. Let's say it's not W, it's, let's say D, it's W. Fine. So it is W tilde 1 updated value, and W1 is actually, it is equal to 1 by 3 e to the power minus alpha divided by 1 by 3 e to the power minus alpha plus 1 by 3 e to the power alpha plus 1 by 3 e to the power minus alpha. So basically uh, it is 1 by 3 will be common, so it is e to the power minus alpha divided by uh, e to the power, or 2 times e to the power minus alpha plus e to the power alpha. Similarly for x2, what is the what should be the value? Okay, I think w1 of 1 here, or I think the w1 of 2. It's what? E to the power alpha divided by 2 times e to the power minus alpha plus e to the power alpha. And w1 for the third point, it is e to the power minus alpha divided by, fine. Is that okay? Like that you do.
Yes, sir.
So calculations, don't worry about it. Might, this calculation might be wrong, but the essence of it is, uh, how do you get these weights, right? You take these weights and then you take the average of it and use that to classify. Is that fine? Maybe you can go through this once, the lectures once, and maybe in the solve with us you can see the examples like this to solve. Might be, but this is the algorithm. I hope you understand the algorithm,
Yes, sir.
right? So what is the algorithm here? You take the weak learner. Weak learner in this case is a decision term, right? You assign uh, some weights, right? Some weights initially and to the all the data points, let's say, and uh, the weight should be, it's like 1 by n, right? So if you have n data points, the weight has to be 1 by n. Then how do you update these weights in the each iteration based on this rule? If you do the mistake, you add more weight to that, and if you don't do the mistake, you reduce the weight from there. Fine. And then you do it like till when? Till your this decision stumps, right? That will give you the correct answer. So finally what will happen? So what do you think in this case, x1, x2, x3, it was actually doing wrongly on this, right, and doing correctly on these two data points. So what do you think, the weights for these points will go higher and or 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 lower? For this point the weights will be lower, right, and the weights will be higher to
Yes,
this.
sir. Lower.
And then it should finally after some iterations, right, it will give me the correct weights, so that they should be able to properly classify the decision stuff, right, should be able to properly classify that.
If it is correctly classified, the weight will go down. Na?
Yes, it will go down by this algorithm, but it is not like hard and fast rule like that. You can change it, but a basic algorithm is like this, correct? This is dependent on you, right, how you wanted to apply that rule. If you apply it, let's say h of xi is equal to yi, if I wanted to increase the weight for that, but in general we don't want to give more weightage to that, right? If you are correctly classifying, we don't have to worry about it, right, like that. Correct. So if you are correctly classifying, your weights will go down, and if you incorrectly classify, the weight will go up. Fine.
Yes, sir.
Yeah, I think, see, it's a bit of different scenario, right, and it's not like very detailed in the lectures also. But I hope if you go through the lectures, it is not much difficult to understand all of this. I haven't gone like outside of the syllabus anyway. It's like same whatever sir has taught. But you should go through it once more, right? You should go through the lectures once more so that you'll understand, and you should see some examples over that, all these concepts, and after that I think you'll feel confident around those concepts. Fine. So that's it from week 11. uh, yeah, any more doubts if you are having, right, you just go through the lectures and the notes again. Maybe you can solve with
Sir,
us.
the lectures in the last weeks are not very, very convincing.
Your voice
Very,
is not clear. What are you saying?
the lectures in the last few lectures are not very understandable. It's
Yeah,
like
yeah,
that.
so it is kind of, it's not like very connected to the previous concepts. One thing I feel like that, and it is like very short description, right?
Yes.
So that will
Sir,
Yes, sir.
the last thing that you explained, what is the main formula there? That if it is correctly classified, then one formula, and then if it's not classified, then e to the power minus, I guess.
yes,
Minus
yes,
alpha.
yes,
So using those two, we can solve, right?
yes, yes.
Yeah, yeah, okay.
Yeah, no, when you see the examples, right, I think we'll see those examples, and I think we'll be able to
Yeah,
solve.
when will we solve those questions on this?
Yeah, 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 yeah. Fine. Okay.
When will we?
I think we'll have the session. I think it is not mentioned in the okay. It's on a Friday.
It's on
Week
Friday.
11, 12 solve with us. Probably I'll take that session. That time I'll explain through the examples. Fine.
Okay, okay.
Yes, sir.
Okay then. We'll stop here now. Thank you guys. Bye.
Thank you, sir. Good night.